Hi, and welcome to statistics. This is the second semester. We're going to start off with 6.1. This is experiments, good and bad. All right. So first of all, this is kind of a review. Observational studies, if we remember, is something that you observe. You can record variables or you can even measure variables, but you're not allowed to actually interfere with those. The examples would be you could count, how much of a specific type of wildlife there is in an area. You could take a bunch of pairs of twins and see how they do on standardized tests, and you could compare them. You could look at weather trends. There's a bunch of things that you can do that are observational studies. And if you remember, we talked a lot in semester 1 about experiments as well. This is where we actually do change a variable to see if it will affect the results. There are two variables in an experiment. We have explanatory or what's called independent variables. Those are usually our x's. And if you remember when we did linear regression, that's when we did all those online graphs with the lines. What we're looking for basically in explanatory is the x-axis is what is actually changing that might cause a response in the y variable. And that's why the y variable is called a response or dependent variable. Some important definitions you need to write down. Subjects of an experiment are the individuals who are studied in an experiment. And a subject does not have to be a person, although it could. If you were going to test medication on people, then of course subjects would be people. But if you're going to see if watering or give a certain plant food to a plant would make it grow better, then your subject might be plants. It could even be mechanical. So maybe your subject is airplane parts, and you see if you use a certain kind of oil or if you service it so many hours, if it lasts longer, then your subject might be an airplane part. Treatment is any specific experimental condition that's going to be given to that subject. So in our example of the people getting different medicines, that would be the medicines would be the treatment. And in our plant example, getting a certain type of amount of water or getting a certain type of plant food would be the treatment. Sometimes it's hard to tell the difference between an observational study and an experiment because it may sound like one, but it really is not. So let's look at the two. For number 1, we have students sign up for a history class online or in a traditional classroom. At the end of the semester, we see who has a better average. In step 2, we have randomly assigned 2 groups of students. Some will take a history class online, others will take a normal classroom. At the end of the semester, we see who has a better average. So it sounds like these are basically the two things. We have people doing a regular class and online, and we're trying to see who does better. But if you notice in number 1, nowhere did I say that we were going to put people in a certain class. They got to decide. Notice how it says students sign up for. So they get to pick if they're online or they're traditional. This is an observational study because we did not force them to do one or the other. In number 2, though, if you notice, randomly assigned 2 groups of students, that means now I have chosen. So student A has to take history class online and student B has to take this history class in person. So they didn't get a choice in the matter. That means I'm affecting the variables, so that means number 2 is the experiment. A clinical trial has to do with medication and the medical field. These are experiments that study the effectiveness of a certain kind of medical treatment. Now, it can be medicine. That's something we always think about. Oh, should you take pill A or pill B? But it could also be, if you think about like cancer treatments, maybe it's a type of chemotherapy or radiation treatment that they think might work better. Placebo is something we've talked about before also. This is a treatment that has no active ingredient, and sometimes it's called a sugar pill. And the placebo effect is actually a real thing. Sometimes patients report feeling better after they've been given a placebo. So even though they didn't get any medicine at all, they just got a fake pill, their brain basically has talked them into feeling better. Okay, so we're going to read this example, and then I'm going to go through the different things that are there. A researcher wants to study the effects of price promotion on a consumer's expectations. They basically have some kind of video game. And for two different groups, they made up two different price histories. For one group, they had basically the price the same, almost like for basically a whole year. Every month it was the same price. But in the second group, they had a normal price, but then every once in a while there would be a sale or the clearance or something like that where the price would fluctuate. So then they asked these economics students what price they would expect to pay for the video games. So we're going to go over to the whiteboard and talk a little bit about what we saw. So for our example, is this an observational study or an experiment? Well, hopefully you notice that it is an experiment because I basically took two economic groups of students and I told them one history and I told them the other. Remember, this isn't a true history of the video game. It's a made-up one to see what their expectations would be at price. So that was experiment. The explanatory variable, remember, is what we're changing. This is what is told about the price history. And the response variable, so this is kind of like what we're trying to see, telling these kids the different price history. What are we trying to see as a result? That comes right here. What would they expect to pay? So the money they would expect to pay is the response variable. The subjects, who were we testing on? Well, we had two groups of economic students. So we would write two groups of economic students. And treatments. Treatment one was that they were told the price history was basically the same, and treatment two was that the price variable is differing. So one treatment was price the same, and the other one is that the price differs. And as you could probably guess why they were doing that is if the price stays the same, then a student would expect, well, hey, that's the price, and so I should just expect to pay that. But if the price differs, and so normally it's $100, but sometimes you can get it on sale for $70, and sometimes you can get it on sale for $50, and sometimes it's $85, then the student may not expect to pay $100. Maybe they'll say, oh, I'll just wait until it's on sale, and then I might actually pay $70 for it. So you can see how the different treatments made the responses different with our kids. Now, in our experiment that we talked about people doing online classes versus an in-person class, the first one, which was an observational study, we let the kids choose. Now, the issue with letting people choose is if you know you hate online classes, you're probably not going to sign up for it. If you know you really love to do class in your pajamas, then you would definitely sign up for the online class. So when I don't do the randomness and I don't assign people to it, there's a little bit of variables that are getting hidden into my observational study that I might not have thought about. So if everybody who is doing an online class is really organized and they always do their homework so they can always, keep up with the online class, they may actually do better than kids who are in person. And maybe they were in person because they need somebody to tell them, hey, do their homework. Hey, do your homework. So randomness is a very important part of our whole procedure. So we always want to randomly assign our treatments and our subjects, or we introduce bias. And if you remember on your TI-84, you can use random integer or the randint command to get a random thing. There's also the random number table in the back of your book. So anytime you randomly select somebody, you need to tell me, okay, I'm using the calculator or I'm using the back of the book. Here's a very good example of somebody who set up an experiment. I have 100 patients who will be on a trial for a weight loss pill. I assigned each person a number between 0, and 99, so that's 100 people. I use a random number generator to get numbers. The first 50 numbers that I pull by that generator will be people who get the real pill. The rest of the 50 people that I don't pull will get the placebo. Now, I should also put in there that if I pull the same number twice, we just skip it and keep going on. And then the other important thing about this experiment is I'm not going to tell the patients which group they're in, because that can introduce that whole placebo effect. So if I tell you you're getting the real diet pill, well, then maybe you'll just lose weight because you're expecting to. So when we design an experiment, which is the whole point of this lesson, first of all, you have to remember to always randomly assign your groups. You cannot say, hey, who wants to be in group A? Because then, you've introduced some kind of bias. Make sure you control all other variables. So if I am testing who's going to do better online versus in person, I should probably have the same teacher for both online and in person, because if I have different teachers, or I use a different textbook, or if I make one test really hard and the other test really easy, you can see how that might change my results. Make sure you use enough subjects. Remember, subjects are who we are testing, and so we want to have a big enough sample size. So in my classroom experiment, I don't want one online student and one in-person student, because if one student, has a bad day, or, something happens and they get sick, our answers are going to be very, very skewed, because, that one person is basically 100% of the people in that group. So you want to make sure you have plenty of people to do your experiment on. Okay, so this is what we are going to be playing around with. This is called diagramming an experiment. And there's some important things I want to point out. First of all, normally we start with volunteers, because normally we don't tell people, hey, you have to be in an experiment. And you can break it up however you want. Sometimes we don't even break it up. Sometimes we don't divide male and females. You could do it as high school students and college students. You could do it 9th and 10th graders. You could do it really any way that you could break people up. Or, like I said, you don't have to. There we go. This next word is important. You always need to write random when you start deciding who gets what treatment. So you notice for males, I don't randomly assign who's a male. Hopefully that's already decided. But I do randomly decide, once I have males, who's going to get the treatment and who's going to get the placebo. Down here, the females also, you had to write random again, treatment and placebo. And then what we always do at the end of a diagram of an experiment is we draw lines and we write the word compare. And that's just letting us know that these are the things that we're actually going to be comparing between each other. Notice that on this line I write what the treatments are. This is 500 milligrams and this is placebo. Same thing the females get. All right, let's do an example. Can aspirin help prevent heart attacks? A large group is interested in this information, so they design an experiment. 11,037 took aspirin every second day, while 11,037 took a placebo. After several years, the study found that subjects in the aspirin group had significantly fewer heart attacks than the placebo group. So first of all, the subjects are the 22,074, I think, people who volunteered, because we basically added those two numbers together. The explanatory variable is taking aspirin or taking a placebo, and the response is how many heart attacks somebody had. All right, so we're going to create our chart over on this whiteboard. So remember, we always start with the word volunteers, because nobody got made to be in this experiment. They didn't divide it up by males or females or anything like that. So you're going to just have two lines. And we're going to put random, because remember, we randomly chose who got to be in each group. Treatment 1 is the 11,037 who what was the first one? Took aspirin. And on this line, there was 11,037 people who took a placebo. So compare this to the last one we just saw that was pre-made. We have volunteers. We didn't break it up into male and female because nowhere in the experiment did it say to. We have random. Up here, I write what the first treatment was, and if they give you the number, write the number. And down here, this was the placebo, and they did give me the number. And that's really all there is to it, except for the last thing. If you remember, we always finish up our diagram with the word compare. So you need to remember that word. So volunteers, random, and compare should be in pretty much every single diagram. And then this is the number that's going to change, and the number of lines may change because maybe I have somebody who has a strong aspirin, a weak aspirin, and a placebo. Then it might have 3 branches. Now, if you think about doing an experiment, if you flip a coin 10 times, sometimes you're going to have 7 heads. Sometimes you're going to have 3 heads. Sometimes you're going to have 5 heads. You may even get 10 heads. So every time you do something with an experiment or even an observational study, even if you control it, you're going to get results that are just kind of all over the place. However, when we have a controlled experiment, at some point, the difference is so large, and if we've had enough people that we've tested, that we might conclude, hey, what we're seeing is not by chance. There actually is a difference. So if you flipped a coin 10 times and you got 9 heads, you may not think it's unfair. But if you flip that same coin 1,000 times and 999 times it was heads, you may think something's up. And you would be right, because at that point, there is significant evidence that that coin is unfair. Same thing with our treatments. So if I give somebody aspirin and somebody a placebo, and so many more people with placebo had heart attacks versus the aspirins, it would be a pretty safe bet to say, maybe the aspirin helps with blocking heart attacks. And maybe you've actually read studies or heard that people who are at risk for heart attacks should take aspirin. And that's why they did studies on this. The word that you need to memorize is statistically significant. It's underlined right here. This is what happens when we find a difference between a group, our control group, like the placebos, and the experimental group is so large that we can't just say, oh, well, that was just an accident. So you start seeing, 20 people had a heart attack out of this 11,000, and maybe 500 people out of the placebo out of 11,000 had a heart attack. You may think, oh, wow, that's such a big difference that maybe the aspirin really does help. Now, we do know that experiments are the best way, and that's actually how we determine causation, okay? But sometimes you cannot use an experiment because it's just not possible. Some examples I put in the parentheses: you can't make somebody have a heart attack. I mean, you could stick a defibrillator on them and give them a heart attack, but that's not really ethical. And you can't also tell people that they need to text and drive because you have to do an experiment on them. You're basically putting their life in danger in either of those circumstances, and it's really not ethical. So when ethics are a problem in forcing people to do certain things, you have to have a good observational study. This is what you have to have for a good observational study. First of all, it's got to be comparative. So you might randomly select who is in your group or what kind of items you're going to be looking at. You have to use matching. So if you go around seeing who texts and drives, and you ask people, and then you ask people who don't text and drive how many accidents they're in, you can't just stick everybody in a big pot and just compare it. You got to kind of divide it up. So you could try teenagers who text and drive versus teenagers who don't. Young adults who text and drive versus young adults who don't. Or older people who text and drive, which I don't know how many do that, and then older people who don't. Then you could kind of start seeing what happens in the age groups as you text and drive. Does the amount of accidents of texting and driving increase in all age groups? If so, that's a pretty good indicator that maybe it's the texting and driving that's causing the extra accidents. Confounding variables is something we talked about before Christmas break, and that is something else that's going on. We use the example of people in third world countries have less TVs than people in America. And they also have in third world countries, they die a lot younger than the United States. And so we said, is it reasonable to say that owning lots of TVs will make you live long? And we said, well, no, not really. That doesn't make sense. The confounding variable there is TVs cost money, and so if you have money, most likely you could afford health care or go to the doctor when you're not feeling well. And so the confounding variable there is the money or the ability to get health care. And that might actually cause the problem that we're seeing, not just the TVs. Another example is church attendance. They actually did studies, and they say people who attend church tend to live longer. Maybe it's God blessing them, but at the same time, maybe they don't smoke. Maybe they don't do illegal drugs. Maybe they live a more cautious life if they're going to church. And any of those might take into account why somebody might not live or might live longer on average than other people. An example of testing for gender bias in treating heart disease. We can't give somebody heart disease. We already talked about that. But we have found that women are given less aggressive treatments for heart disease when compared with men. And so when you first hear that study, you may think, wow, doctors are being unfair. Why would they give a more aggressive treatment to males than females? Because a more aggressive treatment is going to give you better chances of living. Well, it turns out that if you did more research into the problem, that the doctors weren't being sexist at all. You probably know that men get heart attacks at a younger age than women. It's around 40-ish, I want to say, that guys' risk for heart attack starts to go up, whereas females, it's not until maybe 60 or 70. I can't remember the exact age. But anyway, if you're 40, you're relatively young, and so you can afford to take more aggressive treatments. But if your first heart attack is not until you're 60 or 70 or maybe even 80 years old, maybe there's other things going on. Like maybe you have diabetes, or maybe you have maybe you've had cancer, or maybe you have weak bones, or something else might be going on just because you've gotten older. They can't really take a stronger treatment, so they have to go with a less strong treatment. So that's an example of a confounding variable where at first it looks like something's going on that's maybe not right, and then at the end it turns out it really wasn't. It's just there's some other things going on. Okay, so that is it for section 6.1. You are now ready to find your assignment and get that done.